Okay, Matt Roscoe here at the University of Montana with a lecture on our chapter 10.1, Taylor Polynomials in Calculus 2. Let's get started. I want to tell you a little bit about motivation and then take you through a derivation of a Taylor polynomials of degree 1, 2, and n for a particular function. And notice that that'll be all near zero. And then we'll do a few examples of generating Taylor polynomials. And then we'll talk about new motivation and then deriving a formula for Taylor polynomials near x equals a, and one more example and end. So the motivation here is that in the study of mathematics, some functions are easier to work with than others. For instance, if we're studying rates of changes, typically polynomials are easy to work with because they're just easy to differentiate and integrate. They're also easier to compute, so technology can deal with them a lot more easily. And that leads to the question, how can we approximate a function, that is any function, using only polynomials? So that's what we're doing today. We're approximating functions with polynomials. In particular, this approximation method or methodology leads to a type of polynomial called a Taylor polynomial. And so you'll hear me referring to it as Taylor polynomial. So suppose we wanted to approximate the function f of x equals cosine x near x equals 0 using a linear function. How would we proceed? Let's take a look at the cosine really quick. So this is what the cosine looks like, of course. So if we're approximating near x equals 0, that means we're approximating the function in this region, right? Around 1, 0, comma 1. So we're trying to approximate the function in this region with a linear function. And so you can see that if you zoom in really close, that a linear function would do well to approximate the behavior, it looks like, from about negative 0.02 to positive 0.02. So the question is what is that function? And you might know it just by looking at it, but let's just pretend we don't know it and see if we can go through a process that would lead to an approximation there. Okay, so I'll go ahead and get my Elmo cam out and we'll start talking this over. Okay, so here's the idea. We have a function f of x equal cosine x, and we have an approximation, and the approximation we want to be a linear function, so I'll call it a polynomial degree 1 function, since we're after polynomials eventually. And a linear function is an example of a polynomial. And if it's degree 1, it has form c0 plus c1 times x. So the idea here is that this is your y-intercept and that's your slope. If you're used to y equals mx plus b, what you're looking at here is y equals b plus mx, right? So one thing that might be important is for the behavior of the approximating function to be similar to the behavior of the function itself. And in the language of calculus, that might mean rate of change, right? So in other words, if I think of the derivative of the function, well, that's easy to get. It's negative sine x. I would like it to be similar to the derivative of this first degree polynomial function, and its derivative, of course, is just c1. So now we've got a function, right, and a derivative, and the question is how can we use this information then to find what the right c0 and c1 are? Well, this turns out to be a question of, well, for what x, right? I mean, obviously this guy's derivative changes in value depending on x, and so this one should respond accordingly. So let's take a look. We have to choose an x, and in this case we've already chosen it. We've set it x equals 0. So at x equals 0, what happens? Well, we know that the function's value at 0 is just going to be the cosine of 0, and that's 1. And we know that the function's derivative at 0 is going to be equal to the negative sine at 0, and that's just 0, right? And that should be the same, the behavior over here. So p1 of 0, in other words, the polynomial valued at 0 should just be, well, the 0 times x, c1 times x will go away, and I'll just get c0 there. And p1 prime, or the derivative of the polynomial at 0, well, there's no x to plug in, so it's just c1. And you can see, equating, what do we get? We get c1 is equal to 1. C0 is equal to, we want C0 to be equal to F0 equal to 1. We want C1 to be equal to F prime at 0, which in this case is equal to 0. Does everybody see how that works? So I want this value to be the same as that value, right? But that value is just the derivative of the function. I want this value to be the same as that value, but that value is just the function evaluated at 0. So we get, for our polynomial, remember the polynomial that we're after, the big question is, what is this C0 plus C1x? Well, now I know C0 and C1. And this is the first degree polynomial. C0 is going to be 1 plus 0x. So this thing is the same thing as P1x equals 1. So in other words, big surprise, we just have a polynomial valued at 1 always. Let's take a look at what that looks like. So I'll call that P sub 1 of x and set it equal to 1, and sure enough, like, that seems to be the right function, you know, in terms of the best line to approximate cosine x in the neighborhood of x equals 0. So it's just the constant function. Let's make these things dotted, I guess, or dashed, so we can tell them different. And let's make this thing really, I guess, thick. I don't know, say 3 or something like that for line width. Maybe even more. 5, there we go. So there we have it, that your first Taylor series polynomial, it's the Taylor series polynomial degree 1 function approximating cosine x in the neighborhood of x equals 0. It's just the constant function 1. And we got it by equating the value of the function and the value of the polynomial at 1, as well as the value of the derivative of the function and the values of the derivative of the polynomial at x equals 0, right? I think I said x equals 1 last time, but x equals 0 is where we're at, right? Okay, but we can see that really this does well very closely into, you know, close to x equals 0, but not very well once we get further away. So we'd like to improve it, and that's where we go next. But before we do that, we should probably just generalize what we did, so in case we can find you know, a general pattern here. So generally what happens if we're centered at 0, you can see that C0 is F0 and C1 is F prime of 1. So generally this guy right here, P1 of x, is generally equal to F of 0 plus F prime of 0 times x. And that should make sense to you, right? If we're going to build a polynomial that behaves like the function, it should have the function same intercept at 0, and it should have the function same slope at that point. And so that's what we found. So just a statement there that says, in general, we can approximate a function f of x near x equals 0 using a linear function according to the following rule. We want f of x to be approximately equal, you know, in the neighborhood of x equals 0 to p sub 1x, meaning the polynomial degree 1 that's equal to f of 0 plus f prime of 0 times x. And we call that approximation the degree 1 Taylor polynomial centered at x equals 0. All right, let's go after the next question because it's more interesting. Suppose we wanted to improve the approximation of the function f of x equals cosine x near x equals 0 using a quadratic function. How would we proceed? So let's just go back to our picture. I mean, certainly we should be able to get something to fit in here that's better than a line, and a quadratic comes to mind because it's parabola shaped and it looks like we could get a parabola to fit in there somehow. And we sort of have a technique, you know, had a technique by equating derivatives. Let's see if we can extend that to that strategy to create a polynomial that's a quadratic, that is a parabola. So I'll slip over to my doc cam. Guess I'll call that page 1. So page 2. Let's see. So let's try to repeat the strategy here. So we have the function. Again, the function is f of x equal cos x, and the approximation, and there the approximation is going to be a second degree polynomial. So c sub 0, no x, so the constant plus a linear term plus a squared term, right? So this would be a second degree polynomial, what we think of as a quadratic. We're writing them kind of differently. Usually we put the x squared out in front and then the linear term in the middle and the constant off the end. But as you can see, that things are growing in this direction in terms of increasing degrees. So we've just swapped directions a little bit. So obviously we want these two to agree at x equals 0, but we'd also want the derivative to agree here. So the derivative of this is going to be negative sine x. And the derivative of this guy is going to be, let's see, so a derivative constant goes away. I get c1x. Sorry, no, the x goes away, right? Just c1 plus 2c2x. So we'd hope that these would be equally valued at x equals 0. And then the last thing, the second derivative of the function will give us negative sine derivative times cosine. So it would be negative cos x. And here we get p2 double prime equal to just 2c2. And that's it. So at x equals 0, then we can take a look at how these things behave. F of 0 is going to be, well, we already saw that was 1. F prime of 0, we already saw that was 0. F double prime of 0, that's what's new. That's going to be equal to negative cosine of 0. The cosine of 0 is 1, so this is negative 1. And now let's take a look at P2 of 0. Oh, that's just going to be C not 0. P2 prime at 0 is going to be, let's see, 0 goes away, that's just C1. And P2 double prime at 0, that's going to be 2C2. And just equating these things, I can see that, again, C naught is equal to F of 0, which is 1. C1 is equal to F prime of 0, which is 0. And let's see, 2C2 is equal to F double prime of 0, which is equal to negative 1. And so what does that tell us? That tells us that C2 is equal to negative 1/2. Okay, so let's take a quick look here and see, we know what C0, 1, and 2 are in our polynomial up here. So that means we can write our polynomial. P2 of x is equal to C naught, which is 1, plus C1, which is 0, times x, plus C2, which is negative 1/2 times x squared. So what that gives us is 1 minus 1/2 x squared, which is certainly a quadratic. It has a negative leading coefficient on the x squared term, meaning it's downward turning. It's got a y-intercept of 1. And absent is a b term, a middle term, where we usually see a b. But let's just see how it fits on Desmos, see if it seems like the right guy. Let's see how this works. P sub 2 of x is equal to 1 minus 1/2 x squared. And boy, that looks really nice. Let's make that guy dotted. Yeah, it seems like it's fitting much better than the line does, especially up here close. Whereas the line starts to deviate, by half. It's by x equal to negative half or positive half. We're quite a ways away, but boy, the parabola looks pretty good in that region. It is a little bit low, but it's definitely a better approximation of the function's behavior around 0 than the line was. So I feel confident that that's a good Taylor approximation. Let's see. Oops. Let's minimize this and talk about what happened here generally. So generally what happened here is we got P2 of x equal to, well, the 1 was the same as f, not f of 0. The 0 was the same as the f prime of 0 times x. And then this is what's interesting here is where did the 1/2 come from? Well, the 1/2 is the same thing as f double prime of 0 divided by 2. So the f double prime of 0 is the -1, and the 2 came to us from, let's kind of go back and retrace it. It came to us from here, from the exponent on the x squared term, which came down as a 2 and then ended up as a 2 in front of the C2, which then became, I guess, a 2 in the denominator down here, right? So we get something like that for a degree 2 Taylor polynomial in general. We can generally calculate them that way, and that's what you'll see on the next slide for degree 2. And now you should be at this point like, okay, I'm getting it. It looks like there's some sort of a pattern here. We get f sub 0, f prime sub 0, f double prime sub 0. We get an x to the 0, x to the first, x to the second. But the big question is what's going on at the denominator in this series, right? We got a 1 down there, a 1 down there, and a 2 down here. What will happen in that third term? So, we should be asking this question, what happens generally, degree n, right? Can you write basically a formula for a Taylor polynomial for any degree? And that's what we're after next. So let's see if we can puzzle this out with one more look at what happens in the third degree. So I'll call that, that's number 3. So again, the function is f of x equals cos x, and the approximation is going to be now a third degree polynomial. Wow, okay, so p sub 3 of x c0 plus c1x plus c2 x squared plus c3x to the third, right? And it's pretty easy to see that we're going to get the same things for C0, 1, and 2. So the big question is what happens with C3. So in order to figure out what C3 is, what we do is we take f prime of x, that's going to be negative sign, f double prime of x, that's going to be negative cosine, and f triple prime of x, so derivative cosine is negative the sign, but it's negative already, so that'll be sine of x. Let's see, so p3 prime of x is going to be, so taking the derivative, we get c1 plus 2c2x plus 3c3x squared. P3 double prime of x is going to give us 2c2 plus, I'm going to leave it as a 3 times a 2 x to the first, and p triple prime sub 3 of x is going to give us just, oh, I missed the c3 here. I want that constant still there. Just 3 times 2 c sub 3. And at x equals 0, we're going to get the same equation, I guess, for C0, C1, and C2, right, for each one of these that we got in the last go round. In other words, we'll get these 3 and these 3. But let's just take a look at what happens to the fourth one. I mean, the one that we're really, picking on is this guy, right? And so let's see, it's f triple prime of 0 is equal to sine of 0, which is equal to 0, and p sub 3 triple prime of 0 is just going to be equal to 3 times 2 c3. And so if I want to solve for c3, what I would solve for is I would say 3 times 2 times C3 has to be equal to F triple prime of 0. In this case, it's just 0, right? But what that gives me for C3 is F triple prime of 0 divided by 3 times 2, which is the same thing as 0 divided by 3 times 2, which here is 0. So it turns out that the third coefficient, I guess, or yeah, C sub 3 anyways, is equal to 0 in this case, which is kind of curious because that means the third degree polynomial Taylor approximation is the same as the second. But more importantly, what it shows you is that generally what's happening is that that power comes down incrementally. It comes down first as a 3 and then as a 2. So what's going to happen in this denominator is you're just going to have a sequence of integers. And so you're always going to have basically a sequence of integers of that that agrees, I guess, with the terms subscripts. So let's just sort of think about what we have so far. I mean, we know so generally what's going on, if we kind of come back here, we know that you know what we want is a p sub n of x, right? We know that the first term is always f of 0, and I should say at x equals 0. The nth order, you know, this is polynomial, a Taylor polynomial would be this f sub 0 plus f prime of 0 plus f double prime of 0 over 2 times, oh, I missed an x here. That times an x squared. And then the x cubed term is going to be this, right? F triple prime of 0 over 3 times 2 times x to the third. And I hope you can see what's going on down here. You know, if we think of this like a 1, you can kind of see that this is 1 factorial. This is 2 factorial, right? It's the same thing as 1 times 2. And this is 3 factorial. It's the same thing as 3 times 2 times 1. And that should make sense because what's coming down, I guess, in each one of these, what's coming in front, I guess, of each one of these coefficients in derivatives is a sequence from the highest exponent to 1, right? So from 3 to 2 to 1 in the problem solving process. So in general, and I'll put a dot, 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 what we get is we get f n, so the nth derivative evaluated at 0, all over n factorial times x to the n. So that's the way this thing is working. And one thing I wanted to point out too is that this is 1 factorial, but it also turns out that putting this over 1 is also 1 factorial, or is also agrees with this because this is the 0th term, right? We have 0 derivative, we have x raised to the 0 here, and it turns out that, you know, aside 0 factorial is actually equal to 1, so is 1 factorial. So that allows for both of these to be 1s. So just a little aside. So this is kind of neat because now you know, I can get a sense of any polynomial to the nth degree by just doing enough derivatives evaluated at 0 and putting each of them over a factorial argument. So maybe what we should do is just find the next polynomial. We found that the third polynomial, sorry, the third degree polynomial that approximates cosine was the same as the second, and that's primarily because c sub 3 is 0. But let's find c sub 4. C sub 4 should be equal to f, the fourth derivative evaluated at 0, all over 4 factorial. And let's see what we get. So let's see, the third derivative is the sine, so the fourth derivative, f sub 4 of x, is the derivative of the sine, and the derivative of the sine is the cosine of x. So f sub 4 evaluated at 0 is going to be 1. and I guess 4 factorial is there, so that means that the polynomial, Taylor polynomial, 4th degree, that approximates the cosine here is going to be the same one that we've seen so far, right? So it's going to be this 1 minus x squared. So I guess what would be 1 plus 0x minus x squared over 2 plus 0x to the third, because we found that that was 0 in the last one, and then plus this value, f sub 0, the 4th derivative evaluated at 0, which is just 1 over 4 factorial times x to the 4th. And I guess now we can kind of see this as a factorial if you like. 2 is the same thing as 2 factorial. So the polynomial 4th degree Taylor polynomial approximation of the cosine function is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. I think you can kind of see how this is going to go. These are going to go up by 2 each time. We're going to miss 1 every other time. So let's take a look and see how this fits on. So we know that the 3rd degree Taylor polynomial is the same as the 2nd. Nothing interesting to plot there, but let's do p sub 4 of x, and we were told that that's equal to 1 minus, let's do it, x squared, oops, minus x squared divided by 2 factorial plus x to the 4th over 4 factorial. And I don't know how you feel about that one, but let's put it in a different color, say green, and make it dotted. But now we can see an even better approximation of the sine curve, sorry, the cosine curve by the green 4th degree Taylor polynomial. So we're progressively getting better the more terms we add. It turns out that we add a term every other term, and that's because of the alternating derivative valued at 0 for cosine. But certainly the green graph is better than the black one. I mean, if we zoom in on this, we can see the green graph does really well. I mean, now past 1, right? Whereas the purple one was only good here and very close, and the black one was only good to say about I don't know, a radius of about half. Now the green one, at least eyeballing it, seems to have a radius that's much wider, definitely greater than 1, where it's a good approximation. So that's the idea, that we can approximate a function around a point using a series, and those series are called Taylor polynomials, and we've just derived the one for cosine. Let's see, let's go back to. So here is a graphical version of the algebra we just completed. This is kind of a neat thing to see, and let me just show you what we got here. So if we take a look at this calculates and graphs Taylor polynomials. N controls the degree, A controls the center, and f of x controls the function. So I have it set up for the function that we were investigating, cosine. The degree of the Taylor polynomial does include a 0 degree. We started with the 1st degree polynomial. It turns out the 0 and the 1st degree polynomial are the same here. The 0 degree polynomial, of course, is just a constant polynomial. And the center's at 0. You can either type the center in or grab the slider. But the thing that you'll want to look at is, sure enough, there's the Taylor polynomial that we got when we chose a 2nd degree approximation. Now the 3rd degree, notice it doesn't change. It's the same as the 2nd degree. That's because that coefficient on the x to the 3rd power was 0, right? But then when we get to the 4th degree, we add exactly the thing that we found. It was x to the 4th over 4 factorial. Ask yourself what will happen next. Will n to the 5th be different or the same as n to the 4th? Or I should say as the 4th degree polynomial. And hopefully you said same, because just like we skipped over the third power, we're going to skip over the fifth power, and so the sixth power will get better. And now you can kind of see things are really starting to get good. The radius of convergence seems like it's out to 2-ish now. If we go to the seventh power, no change, but the eighth power we get something that's even better. And now radius of convergence seems like we're out in the region of 3. Ninth power is the same. 10th power, now the radius of convergence is well past 3, it seems like. 11th power, no change. 12th, now we're back. Radius of convergence is definitely out past 4. Things just keep getting better and better as we go out more. And notice that we get a sequence, a series that looks very familiar to us from our previous study. Something that obviously must be converging when x is equal to 0. And in the neighborhood, of radius, according to how many terms we add. But it's just fun to watch this thing work. Turns out that for this particular polynomial, the radius of convergence is infinite. If we just add enough terms, and you're getting that sense here, right? If we just keep adding terms, we can get as close as we like to the the cosine function by just adding enough terms. So there we go, out to 30 terms. That's as far as the computer is sort of comfortable calculating without a big time lag. But that's the idea, right? Is we are approximating that function using a Taylor polynomial of differing degrees. One more time. You should really play with this. Come and grab it. You should also use it in your homework. This allows you to find any answer you want by putting in the right function here. So use it liberally as you practice your writing these polynomials. I think it's a really good tool for you to get a sense of whether you're on the right track or not. Okay, so I'll put that away and just say, in general, this is what happens, and this is just what we wrote down on our, or just what we discovered, right? That we get something that's generally written in this term, this way. You take the nth derivative evaluated at 0, put it over n factorial, and that is the nth constant in front of the nth term, I guess, in the polynomial. So that's it. That's really the way this works. Let's just do this quickly and more quickly this time for an nth degree, a fifth degree Taylor polynomial approximation of the sine of x. So something a little bit different here. Instead of the cosine, we're going to get the sine. But you should be thinking to yourself, well, if this was a fourth degree, I'll write it down, fourth degree Taylor polynomial approximation of, let me get this out of the way, of f of x equal cos x at x equals 0. So if this is what cosine looks like, we should expect something somewhat similar to this for sine, right? I mean, these functions are related to one another. They're just phase shifted, right? So let's see if we can figure that out. We'll go after that next. Let's see. So this is number 3, right? Or is it 4? Well, I'll figure that out later. Let's see. So let's see. F of x is equal to sine x. And what we want is we want a fourth degree Taylor polynomial approximation. We know those Taylor polynomial approximations involve derivatives, and we need up to the fourth derivative. So I'll call this, the first derivative will be cos x. The second derivative will be the derivative of cosine negative sine x. Let's see, the third derivative, derivative sine's cosine, so negative cosine x. And the fourth derivative is going to be Derivative of the cosine is the negative sign, so this becomes positive sine of x. And the fifth derivative is going to be cos x again. Okay, I'm going to pause here to get. Okay, so we have all these. Let's evaluate them at 0. So f of 0 is going to be the sine at 0. The sine of 0 is 0. First derivative evaluated at 0 is going to be the cosine of 0, or 1. The second derivative evaluated at 0 is going to be the negative the sine of 0. That's just 0. The third derivative evaluated at 0 is going to be negative the cosine of 0, so that'll be negative 1. And then we're back to sort of where we were here, so that makes that easy, right? Fourth derivative evaluated at 0 is just going to be 0. Fifth derivative evaluated at 0 is just going to be 1. So kind of, you can see these run in cycles, right, of 4 that have to do with this cycle of 4, right? Okay, so we have all of those pieces, you know, I guess that makes it pretty easy for us to go after this, right? We know that the fifth degree polynomial approximation of the function is just going to be f of 0 plus f prime of 0 times x plus f double prime of 0 all over 2 factorial times x squared plus f triple prime of 0 all over 3 factorial times x to the third plus, I'll put it down here, f, I don't know, I should have done numbers up here, I guess. Fourth derivative evaluated at 0 all over 4 factorial plus fifth derivative, oh, and I forgot my x to the fourth there, plus fifth derivative evaluated at 0 all over 5 factorial times x to the fifth. So I'm just plugging into the general form for the Taylor polynomial series, and now I can just pull off the constants that I need up top here. So let's do this. F sub 0 is 0, so that means this first term is just 0. The second term is 1 times x, so I just get an x there. The third term is negative 1, so it'll be minus 1 over 2 factorial, but we have it times an x squared, so I might as well just compactly write this as x squared over 2 factorial. Oh, wait a minute. The second term is 0, right? Sorry. So f sub 2, this piece right here, right, over 2 factorial, that's 0. So I don't have any x squared term. So just sort of maybe this will be easy for me to make it easier on you. I can see I have a 0 there, a 0 there, and a 0 there, which means I have a 0 here, a 0 here, and a 0 here. So the only surviving terms are this term, which I've written down, then this term will be next. It's this value, negative 1 over 3 factorial. So I'll have x to the third over 3 factorial. And then this term, which is that term right there, so it'll be 1 over 5 factorial. And I guess we would have an x to the fifth there, right? And so now it sort of seems like it's pretty easy to see what's going on. This is the same thing as x to the first over 1 factorial, x to the third over 3 factorial, x to the fifth over 5 factorial. The next thing I would, I would generalize this. You'd have x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. There'd be no sixth term because of the 0 alternating here, but there'd be a seventh term. It would be negative x to the seventh over 7 factorial. and so on. So it seems like we've used the structure of the Taylor polynomial creation to get a sense of how this series works. Let's go ahead and take a look at how it looks online when we graph it. So let's see, where did my... let's see if we got it right. So I'll use this one instead of Desmos. We'll change this to sine. Let's roll the degree down to 0. So it turns out that 0 degree is just 0. The first degree is quite different than what we saw last time. The first degree Taylor polynomial is just equal to x, which agrees with our first term. The second degree polynomial is the same as the first, and that's because there's that missing x squared term here. But there should be something for the cubic, and there it is, x to the third over 3. Fourth, nothing. And fifth, there's what we got, x to the fifth over 5 factorial. And then we'll get nothing for the sixth, and for the seventh we get an x to the seventh over 7 factorial, but negative. And you can certainly see the convergence here is happening pretty nicely. By the 9th we get something like that. By the 11th we get something like this. By the 13th here. And notice that radius of convergence just growing as the number of terms are added into the polynomial. This is amazing. We're now looking at a 30 degree polynomial. I noticed that actually it's off the screen a little bit, but there is another term in there. Oh no, the 30th is missing, right? The even ones are missing. So the 29th and the 30th are the same. There's a 29th degree polynomial approximation, Taylor series approximation of sine. I hope you're impressed as I am. I just think the technology is incredible to be able to see this. It's something I never got when I got this class in college. And I hope that you'll use this to check your answers. I think it's a good way to get a sense of what's going on and whether you're on the right track. Where to go next? Let's see. What about e to the x? What if we wanted a degree 10 polynomial e to the x? So let's do another example here. I'll switch over to my ElmoCam again. So I should probably wrap this up and just say, you know, this is what a 7th degree Taylor polynomial approximation of the sine, right? F of x equals sine x at x equals 0. All right, so that's on the books. Let's go to 6th page here and talk a little bit about what if we want f of x to be equal to e to the x. Well, this is a particularly easy one, surprisingly, because I don't know if you notice what's going to happen here. You know, f prime of x is still e to the x, right? And f double prime of x is e to the x. In fact, any f of n of x is going to be equal to e to the x, right? So that means that f of 0 is just e to the 0. Anything to 0 is 1, right? And since these are all the same, fn of 0 is also equal to e to the 0 equal to 1. So in the Taylor series approximation, anytime we have a derivative or the function itself evaluated at 0, we get the same thing. We just get 1, right? So sort of going back to the general format, all of these, f0, f prime of 0, f double prime of 0, f triple prime, quadruple prime, fn prime, right? Those are all 1s. So that means that e to the x should just be 1 plus 1 times x plus 1 times x squared over 2 factorial plus 1 times x third over 3 factorial, and so on all the way through. So that makes everything fairly easy for e to the x. Let's go ahead and knock it out and see if it agrees with the online Taylor series grapher. So that means that the 10th degree polynomial approximating e to the x is going to look like f of 0, that's this one, 1, plus f prime of 0 times x, so that's just going to be x, plus f double prime of 0 over 2 factorial, so that's going to be 1 over 2 factorial times x squared, so it'll be x squared over 2 factorial, plus x to the third over 3 factorial, plus x to the fourth over 4 factorial, and you're going to get bored watching me write this, so I'm just going to say all the way up to x to the 10th over 10 factorial, and this thing should be 10th degree Taylor polynomial approximation of the function f of x equals e to the x at x equals 0. So that was fairly quick. Of course, that's only going to happen with the exponential function because it's the only function who has itself as its derivative. Let's take a look and see what that looks like online. I'll scroll this back to 0. We'll change our function from sine x to e to the x. Oops, not to the c. Hit an enter. Move things down. So the 0 degree Taylor polynomial, let's see, first degree looks like that. Of course, that's just the tangent line, right? At 0. And let's just slowly watch this converge. Let's see, I need to click on that. 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's the function that we found. It's a 10th degree polynomial. And it looks like it does really well for positive values of e to the x. In fact, those all look pretty good. It'd be interesting to see much, I guess, wider view of it. It looks like the convergence is much slower here for negative values of x. Let's just go ahead and watch it converge. Slowly it's going back. Do you notice that? It's slowly finding its way to the curve as we increase the degree of the Taylor polynomial. So, but much slower to converge in the negative values, it looks like, than in the positives. Although fairly hard to tell if we're doing as well beyond 5 high up on the graph. We'd have to really zoom out to get a sense of that, and it's hard to tell where it's at in terms of, I guess, say at 10. But I hope that gives you some sense that it looks like we got the right idea, the right answer anyway, using what we know about the general form of the Taylor series, the Taylor polynomial. So here's your new motivation. You know, some functions are not defined at x equals 0. Take natural log of x, for example. It's not defined at all for x less than or equal to 0. And it makes it impossible to construct a Taylor polynomial centered at x equals 0. So instead, we have to adjust our previous result to obtain a Taylor polynomial centered at a different value at x equals a. So it turns out that that we can kind of think of this really similarly to the way we think about the ones that are centered at 0. And let's just prove this. This looks really familiar, right? If the first degree Taylor polynomial centered at a looks a lot like the one centered at 0. We're used to seeing a 0 right here and a 0 right here and a 0 right here, right? Well, let's see why this is. I'll switch over to my Elmo cam. Okay, so here's the idea. Let's try to do this one a little bit more abstractly rather than taking an equation like cosine and using an example to derive our result. Let's say you have some function out here. So this is f of x. And what we're trying to do is find a Taylor approximation at x equals a. And so we know that x equals a. The function has some value which it evaluates at, and that evaluate is f of a. And what we're trying to do is find the linear approximation to that function at a. So in other words, we're trying to find, this line, which we're going to call P1x, the first degree Taylor polynomial approximation of f of x at a. And then let's just play the game again. So we know that P1x is a linear function. So P1x looks like C0 plus C1x. That means that its derivative looks like this. The derivative of this is just C1, right? And so what we want to know is how to value C0 and C1, knowing what f of x is and how it evaluates at a. So if we want to know, if we want this to be a good approximation near a, what we'd like is for this thing, we want P1x, or sorry, P1 evaluated at a, which is going to be C0 plus C1 times a. I'll just call it C1a. We want that thing to be really close or exactly equal to the value of f at a, right? So that would be equal to f of a, right? So in other words, the y value of this function better be equal to the y value of the function we're trying to model at a. So that's the first result we get. And let's see, the second result, we want P1 prime evaluated at a, which is just C1, to be equal to f prime evaluated at a. In other words, we want the slope of the line to equal to the slope of the function. And so that tells us right away that C1 is equal to f prime of a. That's this number. And let's go ahead and see if we can figure out what C0 is. So if C1 f prime of a, if we plug that in, let's call this our first equation, our second equation. Plugging into 1, we get what? Let's see, so we're going to plug C1 is f prime of a right into here. So we'll get C0 plus C1 is f prime of a times a, and that's equal to f of a. And that means I can find out that C0 is equal to f of a minus f prime of a times a. So we've just figured out what C0 and C1 are. So these two pieces right here. We can now plug those two pieces in to get a general form here, right? So P1, the linear equation, is going to be C0, that's f of a minus the derivative at a times a, that's my C0, plus C1, which is f prime of a times x. So there's our equation for P1, but I notice that two of these terms have an f prime of a in them, and if I factor that out and rearrange, what I get here is f of a plus f prime of a times x minus a. And that looks remarkably similar to the first degree polynomial that we got when we were centered at 0. So this is first degree Taylor polynomial centered at a, but centered at I'll do centered at x equal to a. Centered at x equal to 0 looked like this. P1 x equal f of 0 plus f prime of 0 times x minus 0. I mean, we didn't put the minus 0 there, but notice it's very similar, and so I guess it makes good intuition that really all we're doing is we're shifting everything to a new point instead of 0. Now it's a, And if we shift everything to a, then these should evaluate at a, and this term has been shifted to a. And I don't know if you want to think in terms of transformation, but usually subtracting from x within any I guess function, especially polynomial functions, moves everything to the right. So what we've done is literally shifted our point of evaluation to the right a units. So I hope that makes good sense. I'm not going to drive the whole thing, but I'm rather just going to tell you that it's the same, very nearly the same procedure, a little more complicated because we're evaluating functions at a given point rather than at zero. But you'll see that things look remarkably similar to the nth degree Taylor polynomial centered at zero. So here's your equation for the Taylor polynomial centered at a. And we should probably try it out, and I think we should try it out on the one that was the thorny one to begin with, and let's do the natural log. Let's take a look at the natural log. It's a Taylor polynomial. We want a Taylor polynomial degree 4 of natural log, and let's center it at 1. Just to sort of make it clear to you, here's what happens when we try to, use this tool centered at 0, right? And that should make sense to you, right? Because this thing's not even defined at 0, right? So we don't get any approximation. It just doesn't work at all because we need to know the value of the function at 0 and the value of all of its derivatives at 0, and those aren't they don't exist for the natural log. So the question is when we move this to 1, will we get the right answer, both algebraically and then letting the technology lead us? So let's go about this now and see if we can use what we know here. All right. So let's see, f of x is going to be the natural log of x. So we need a list of 4 derivatives here if we're going to do fourth approximation. Let's see, so f prime of x is going to be 1 over x. I'm going to call it x to the negative 1. F second derivative of x is going to be negative x to the negative 2. The third derivative is going to be, let's see, positive 2x to the negative 3. The fourth derivative is going to be negative 6x to the negative 4th. So that's my list of derivatives. I need to evaluate each one of those at a. So let's see. Evaluate at x equal to 1. This is my a in the format. So let's see. F of 1, well, that's the natural log of 1. It's 0. F first derivative evaluated at 1, that's just 1 over 1, or 1. F second derivative evaluated at 1, let's see, that's 1 over 1 squared, but it's negative, so it's negative 1. F third derivative evaluated at 1, let's see, so that's 2 over 1 to the third, so that's just 2. F, let's see, fourth term evaluated at 1, that's going to be equal to negative 6 over 1 to the 4th, so it's negative 6. So we get this sequence for our f prime, f second, f third, f fourth. And then let's just sort of remind ourselves what this Taylor polynomial looks like. So the thing is going to look like you could go back to the form, but here's what it looks like. It's f of a plus f prime of a times x minus a plus f second derivative at a times x minus a squared all over 2 factorial, right? Plus f third derivative evaluated at a times x minus a to the third all over 3 factorial plus f fourth derivative evaluated at a times x minus a to the 4th power all over 4 factorial. So this is the format just pulled from the general equation for a Taylor polynomial. And so putting in what we know now here, a is equal to 1. So what do we get? We get f of a is just 0. So the first term is 0. F prime of a is 1. So we get 1 times x minus a. F double prime of a is negative 1. We multiply that by x minus a squared, and we'll put that all over 2 factorial. So that's the second degree polynomial. Let's see, so the third one, f, we'd have a plus. This term right here is 2 times x minus, oh, I called them a's up here. They should be 1s, right? We're substituting in at this point. Sorry. They should be 1s. X minus 1 to the third all over 3 factorial plus, and then it's a negative 6 times x minus 1 to the 4th all over 4 factorial. And now, you know, we've done the plug-in part. Let's see if we can simplify it and see if we can generate a rule. What seems to be happening. The first term is just x minus 1. The second term is minus x minus 1 over 2. Let's see, the third term is plus. Now we have a 2 here and a 2 buried in here, but it'll be x, and this should be squared, right? It should be x minus 1 to the third over 3 factorial, but the 2's cancel, we'll get just a 3 there. And then this last one is a minus, and then let's see, we get x minus 1 to the 4th. 6 factorial, this is like, has a 2 and a 3 in it, right? But there's a 2 and a 3 in here, so it's just over 4. And it looks like what's going on here is we get something, you know, powers, I guess alternating powers of x minus 1 all over just 1, 2, 3, 4, and so on. So this would be a 4th degree Taylor Poly approximation of f of x equals ln x at x equal 1. Okay, and let's see if that gets us anything even remotely close to what we'd hope on our, let's bump the polynomial degree down to 0. Let's center it instead of at 0 at 1 and enter. You'll notice that moves, these two are tied together. And so now we have it's actually registering something. That's the 0 degree. Here's the 1st degree, x minus 1. Ooh. There's the 2nd degree. And I do like that. That agrees with our result. We see the x minus 1 squared over 2 factorial. And you can see this is, you know, it does seem like it's approximating in a local sense what's going on around 1. But let's see what 2, 3 looks like. There it is. Oh, that's interesting. They do not cancel these. Do you notice that? So we canceled the 2 and the 2 in here and left it over 3. But the way it's written, it just gives you the full form. That's interesting. You can see the negative 6, which is our the value that we got for the f double, you know, the 4th derivative. But certainly, you know, this is what we got before canceling. It looks like we have the right idea. Here's the term x minus 1. It's an alternating sequence. And we do see if we did cancel, this would be a 2, this would be a 3, and that would be a 4, which is what we got in the canceled form. But kind of interesting to notice, you know, what happens here. I don't know if you're seeing this, but the radius of convergence here is much tighter. It's much smaller. In fact, it looks like it's really running into problems when it gets close to 2. And in fact, it just has a hard time converging. And that's something that we'll study more in chapter 10.4 how can we know how well some converge and some don't? I mean, it looked like the sine and the cosine both behave very nicely, that as long as we went out far enough, we would eventually converge. But here it looks like it's sort of seemed like we're up against a wall of some sort at 2. So I hope that makes sense to you. There's some more to study here for sure. And that's really it for today. So I've kept you for more than an hour. I hope that you found some interest in this, and that you've found some tools that you can use on your homework and on the WebWorks. And please don't hesitate to reach out to me if there are questions that you have about Taylor polynomials today. All right, thanks.